Recording in progress.
Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Chandra Thapa from CSIRO Rosetta 61, where he works as a research scientist. Chandra received his PhD degree from the University of Castle in Australia in 2018, and his current works are in the field of privacy-preserving machine learning on resource-limited environments, application of machine learning to security, distributed system security, and network information theory. And today he will talk to us about enabling deep learning in resource-limited environment with data privacy and software security. Thank you, Chandra, and the scene is yours.
Thank you, Mohammed. So let me share my slides. Is it all good?
But it's not, I can see the slides, but not full screen.
Okay.
It's close to this zooming button here. This one, I think.
Yeah, you go for that. You can do it. You do it. Maybe I do. No.
Is it in the presenter mode or is it present?
No, it's just the
Display.
slide screen.
Yeah.
Not even the presenter.
Is it better now?
No, I'm still seeing just the slide without the full screen.
Okay, maybe what I can do is just share a screen and not the slide. Maybe it should be fine. So I'll just share the screen.
If you go full screen, it should go.
Sorry, it went.
Just go full screen.
Is it all good?
I'm still seeing the slide.
Yeah, this one.
Can you go to the next slide? Maybe then it will change.
Okay, you have to
Yep,
drive it
yep,
from
yep.
here.
Yep.
I'm not sure if you can drive it from here. You have to drive it from here. No, it doesn't move.
Yeah, why it's
It's very weird.
yep, sorry for these technical issues.
Yeah, just drive it from here. See. And if you go there, you can now go next.
No, it's not going next.
Maybe
I'll share the screen. Maybe it will be fine.
Yeah, that's fine.
Yeah. Is it better now?
It's in the presenter mode.
Yes.
So if you click swap displays, maybe that should work. It's at the top left, top.
Get that.
Yeah, so the problem is wow.
Yeah, if you want, you can a bit enlarge this and then present like this, because I can clearly read.
Maybe the screen.
Is it
Yeah,
fine?
it's fine now. Yep, it's fine.
Yeah, ultimately. So if we make it in the presenter mode, so we lose the control from my laptop and then we can't control it from the system's laptop. Anyway, so thank you, Mohammed, and thank you, Amin, and the organizing team for this nice opportunity to be here at Monash and then have this wonderful discussion or talk with you all. So today, I'm just presenting our works, two of our works. One, the first part is the enabling deep learning in the resource limited environment with the data privacy, and another one is a little bit different than that one. That's more related to the software security. So once again, I'm Chandra Thapa, working as a research scientist at Data61 CIDO. This outline of this today's talk. So first part, it will be, we'll discuss around these two questions. That means how to preserve the data privacy in deep learning. That means one of the motivations of this deep learning for this, one of the requirements for this deep learning is they are data hungry. That means we need more data, and then for the more data, we need more collaborations. So how to enable those things, and then at the same time, yep, sure. And at the same time, and at the same time is the how to enable these deep learnings into the resource constrained environment. The second part will be on the software security. It will be a little bit different, as I mentioned. That is how to leverage the transfer-based language models that outperform other models in the natural language processing in software vulnerability detection. Let's just get started with the first part, that's split-thread learning. So these are the outlines for the part one. So we'll briefly talk about the federated learning, then split learning, what are the challenges, and then the story about the split fed and the experiment results. Quickly, I'll go through this overview of the what's a federated learning and split learning. So on the left-hand side, we have this federated learning setup. Quickly explaining what the federated, what happens is we have the multiple clients, they have the data, or we can say they are the data custodians. And on the right-hand side, we have the server. And so what happens is the server has the model, the full model, and then it sends the model to the clients instead of taking out the data from the client side and then doing the centralized learning. So it sends the model to the clients that we call the model to data approach, so that the client would not need to send the model from the send the data from their premises, so that always retain their control over the data. And data can be sensitive, like health data. Here, for an example, I put some skin disease images, and then the clients train this model, whatever it receives from the server on their local data, and then sent back to the server. Server it aggregates, and then this process repeats till the model converges. On the right-hand side, we have this split learning. So what happens in this split learning is in the federated learning, we see that each of the clients are training the full model, and if the model is too large, something like this is the usual case of deep learning, then client might not have that computational capacity to run the full model. Instead, what we can do is, if the model is the neural network-based architecture, so we can split the neural layers into the multiple parts, and then we can distribute the computations. For an example, this is the simplest example. The full model is split into the two parts. So the first initial layers will be passed to the client side, and the remaining will be resided inside the server. So let's start how it works in the client zero and server is, so I'll just quickly say the two terms. This in the neural networks, we have this term called forward propagation and backward propagation. So in the forward propagation, it starts with the input, and then it starts computing its learnable parameters into the forward direction till the loss is calculated. And once the loss is calculated, then what we do is we calculate the gradients as its correction to minimize the loss of each of these learnable parameters. And that's where the correction happens in our neural architecture, and that's how it learns. So client zero will have the, so we consider only the client zero and server at this moment, and then we'll go with the multiple clients. Client zero will have the initial few layers. It does the forward propagation, and then that's a part where it splits, or that's the end layer of the client zero. That activations, or we call it as a smash data, is sent to the server, and then server carries the forward propagation till the loss. And then the reverse, the backward propagation, calculating the gradients. And once we have this gradients of this smash data, that's whatever it sends from the client zero to the server. And then the server sends those gradients client 0. Then after receiving that 1, it continues its back propagation. This is how the training happens in between the client and then the server. If there are multiple clients, then what happens is once the client 0 completes it, it sends its model to the client 1, and then client 1 continues its engagement or the model training with the server on its local data. So what might be the challenges? So as I mentioned, so in the federated learning side, the challenge is client needs to run the full model. And for the resource constrained environments, something like with the IoTs, it's really difficult to leverage the excellent performance of deep learning. And then the server and clients, the another thing is at any time, the server and clients have the access to the full model. So from the model privacy perspective, it's a little bit leaking everything, every knowledge about the model. If we go into the split learning, so it somehow address these resource constraint, these limitations by splitting the networks, and also has the model privacy once the model starts. If I'm the other third person, if you see, if I'm the model owner and if I give the one person to the client, one another person to the server, and once the training process starts, the server and the client, they don't know the upgrades or the model of each other's, and that's vice versa. So that's how they have some sort of some level of model privacy retained in this one. But the problem here is they have this sequential training across the clients in a round robin fashion. So that's the another clients needs to be in ideal condition and then wait for the another client to complete. So the question here is, can we remove these challenges and still get the benefits of this federated learning and split learning? And to answer this one, we propose this split fed learning that's as a combine of these both two versions of learning. So in this slide, we'll just I'll explain about the plain split fed learning, and the next slide we'll see about the enhanced split fed learning idea. So the idea here is now the multiple clients, they compute. It starts with the split learning. That means the model is split, and then the initial layers will be. That's the client-side model portion, let's say. And then the remaining portion will be the server-side model portion that goes to the server. The client-side model portion will be sent to all the clients. They compute on their local data sets, the forward propagation, activations in parallel and independent of each other. They send to the main server those activations simultaneously, and main server computes on those and calculates the gradients, back propagation, sends to all the clients. This is how it happens. But the problem here is once the client completes the forward and backward propagation with this main server, and then over its all local data set, then we call it global epoch. And that global epoch, all the clients have different models, as you can see, because they are not communicating with each other. We can allow the communications as well. But the thing is, we need to have some sort of same model maintained over each of this epoch. So that's why we need to have synchronizations at the client side. That's why we introduced the Fed server, and then what the Fed server does is the clients, all the clients sends the client side model person to the Fed server. Fed server aggregates it and send back to the all clients, so that the model across all the clients at the end of each epoch is the same. That means it's how the model is synchronized. What we did, the extra of this split fed learning is it has these features, benefits of both federated learning and the split learning. But how about the privacy? That means because the clients are sending something to the main server, that's the smash data. So there might be some leakage in between this, whatever it sends from the client to main server, those activations. So what we did is we tried to introduce this one additional noise layer to the client-side model portions. This layer can be anywhere. And it's all based on the pixel DP mechanism that's introduced for this robustness of the machine learning layer. So what it does is it can be anywhere in the client-side model. So what it does is just see into the computes on the, that means the previous layer of this noise layer. And it calculates the sensitivity of the activations of this previous layer. That means what the variations in output based on the changes in the input. And then it is scaled down, and then the scale, that scale is used, the sensitivity divided by the epsilon, that's the privacy posit, is used to calibrate the noise based on the Laplacian mechanism, and it's added to the activations. That's how we get the noisy activations, and it propagates to the remaining layer, and then that's how we get the noisy activations from the end layer of the client 0. That's the smash data. And as you know, that's noisy activations are more private than the non-noisy version. That we added this layer of privacy leakages from the client to the main server. And how about the client side? Because clients are among the clients, because they are sending the models to the Fed server, and again, they are getting back. So in that one, so we again introduced this concept of differential private model training that's introduced by Abadis in the federated learning scenario to just stop these membership inference kind of attacks. So what happens is each client, each local sample, we calculate the gradients, and that gradient is clipped, is L2 norm of the gradient is clipped by some amount. And then we added the calibrated noise. And then that's on the this calibrated noise is added on the average of these clipped gradients of each sample inside each of these clients. And then that is used, those gradients, clip gradients are used to the update the models, and the model is, the weights are sent to the Fed server, and then it aggregates and then sends. So this is how it's more private friendly in terms of the gradient objects, because the gradient objects are has lots of things to do with the leakages. So again, quickly going through the notion of the privacy perspective from the split learning side. So the data privacy by default, it's the default privacy that you get is from the model to data approach. Data never leaves the data custodian, and data custodian have the power of its control over the data, and another is machine learning over the split network. That's how the server and client, they don't know about their updates of the model. And then the extra two components that we integrate is the PixelDB noise layer in the client side, and then the model training on the client side with the differential privacy. So we do have various that means variants of the split weight learning, as you see that in my previous explanations that the loss is calculated at the server, but it's not always necessary that loss we calculate at the server, because we need to pass the label to the server. So that's how the leaks happens. And if it's not required, then we can do it. What we can do is we can, in a simplest example, we can split the model into 3 parts. The first part will remain into the first few layers will remain in the client side. The remaining big part will be with the server, and then the final few layers will be again back to the client, so that it can calculate the loss and do this operation. So what happens is process starts forward propagation with the client, goes to the server, and again back to the client, and then back propagation also happens in the reverse direction, client, server, and then the client. That's a U-shaped, we call it U-shaped split learning or split weight learning setup. So both are possible. And in the from the server side aggregations point of view, we propose 2 algorithms. One is the version 1. So what we do is whenever this client in parallel sends these activations or the smash data to this main server keeps the multiple copies to process this forward, backward, and gradients to each clients. And then at the end of each epoch, it can actually aggregate and synchronize its model again. But the thing is, it's not always necessary. We can actually process in sequence. That means whenever the client sends simultaneously all the gradients, all the activations to the, or this mesh data to the main server can continue improving its server-side models. That means it engages with the smash data of the client 1 in the random fashions, then maybe client 3, it's keep continue updating its model. And then we, in the separate work, what we did is we also generalized this split rate learning. That means that any copies can be remain within the server side, because server, if we assume the server is not a resource constraint, then it's possible it can have multiple copies. But if you think about the big models like we have in the natural language processing these days, is the transformer. In the following slides, we'll see they are really big, and then the parameters are really big and might not be it's possible with even with the server. So we have that flexibility to keep how many copies in the server side as well. So this is the simple evaluations of our approach compared to the split learning and federated learning. That means the total training time. It's not the computational complexity analysis. It's just the total time model training time analysis. So if you go into the, if you see into the takeaway message, if you see into the split learning, the second row and the fourth column. So we have this term 2 beta times of modulo of W over R times of K. K is the total number of clients. And this beta modulo W, it's just the size of the models. And beta is just a fraction of the size of the models that is placed into the client-side model portion. So beta times of W is the client-side model portion. And R is just the communication rate in between the client and server. So there is a multiple direct multiple. This term is greater than or equals to 1, and there is a direct multiple of K. So if you have large number of K, then SL becomes inefficient in this sense. So that's how. But if you see in case of SL, our split rate learning, there is no such term, and instead we have the term divided by K. So for a large scale, what we can easily see it is split rate version 2 is strictly less time consuming for the model training than the split rate version 1 and split learning. So we do some empirical measurements of this cost as well. What we did is, because theoretically we say that all the computations associated with each clients are in parallel fashion at the server, but in the implementation, we did some this multi-threaded Python programming to measure the time, so that the time might be different than the theoretical assumptions, but somehow it gives us some reflections about how it looks like. Considering this ResNet 18 and HAM 10,000 and the LXNet on means, so what we can see, it's a split rate version 1 and split rate version 2 are 4 to 6 times faster than the split learning in the same setup, and similar better speed than the federated learning. So if we see, we can see it from the communications side. The right two figures, what we have is split learning, split rate version 1 and 2 have the same or overload data downloads at the upload size. You can see it there, and which is better than the FL for the multiple clients. So what happens is, if we see in terms of communication, so federated learning, it's just the model size. That's the communication between the server and clients. But in the split or split rate versions, it's the activations, it's passing from the client to the server, and then to and fro, and the gradients are passing. So it is dependent on the client's local data size. That's why if you have the multiple many clients, the data is distributed across the many clients. That's how our setup works. That's why you see the communications is decreased, but it remains same for the federated learning. For our more, that means experiments, the data set we consider is 4 popular data sets. The HAM 10,000 is the skin, that's a medical data set, that is skin conditions images. Most of these data sets are quite popular and image data sets. And then model architectures we consider is also quite common in the machine learning domain. So it's from all the convolutional neural network based architectures. So here recurrent based architectures are not considered because we can actually carry on the same, the mechanisms to that means experiment with the split rate learning on those architectures as well. But till now, we don't have any mechanism how to split the recurrent neural networks so far. Though there are some works do that one, but we need the special conditions that's very restricted to split the models in the recurrent neural network. That's why we are limited to the convolutional neural network based architectures. This is the overall performance of the split fade version 1 and version 2. In this one, these performance are in the split fade learning. So these performance are not the enhanced split fade learning. So we just keep the simple split fade learning in the scenarios for the fair comparison. And we see the convergence pattern for this particular example is rested 18 on the HAM 10,000. So they took quite close to each other even with the normal means the centralized one. That's quite good result. But the thing is, it's not always the case. If you see VGG16, what we see in other experiments is VGG16, that's model on CFAR10 did not converge, split learning did not converge, and so happened with the split fade learning. But the fade rate learning has some good that means accuracies, testing accuracies. We also try to see that means how these different clients perform individually with each others, and then we calculate this coefficient of variations of these accuracies that has a performance metrics, and coefficient of variation measures the dispersions, and if this CV value is less than 10, then we can say that these performance are quite close to each other, and we can see from this these plots that these are less than 10 the CV, and then we can see the performance in between the clients are also pretty close to each other if we have the multiple clients. And our experiments we performed is from the 2 clients set up to the 100 clients. So this another experiments we try to see what will happen if we increase the number of clients in this kind of distributed machine learning, we say. So whenever I say distributed, it includes the federated split or split fade learning. So they have this for a particular example. Again, this is ResNet 18 and HAM 10,000 data set. They follow the similar and then close to the our normal, but again, I say it's not the always the case. We can have the different gaps with the normal and then the distributed learning. So as you might wonder at this point, that means what's the point of introducing this split fade learning if they are not outperforming fade learning is split learning? But the answer again, I would like to say it's from this motivation. The motivation is how to leverage the advantage of federated learning and split learning. That's a resource constraint environment, model to data approach, distributed computation, those sort of things. So we leave the improvements of split fade learning as a future works. So this is another experiment that we did where the split fade learning with this enhanced split fade learning on the differential privacy, how it affects this one. So what we did is we kept the client side differential privacy model training this privacy budget constant, and only changed the the privacy budget of this pixel DB mechanism. That means the amount of noise that's added to the activations. That is sent to the server. And as for expectations, the privacy budget, whatever it increases, the accuracy also increases, and then the convergence also it's gradually increasing with the increasing privacy budget. But if we increase the privacy budget, we know that means we lose the privacy. Now let's go back to these. Let's go to the second part, but I would like to pause it here and then see whether you have any questions related to split fade learning or not. Yeah. So,
is there any question from the Zoom? If not, maybe I will ask a question.
Yep, yeah.
In fact, I have 2 questions. Apparently you have combined this split learning and federated learning to get the best out of the both worlds. But My very first question is if the federated server, which sits on the left, can collide with the main server somehow. And if so, are you losing any privacy in that sense? Or there is an assumption that they are not colliding? And
Thank you for this question. It's a nice question. So federated server and the main server. So if the main server is trusted, it's still the task that the federated server does is just the aggregation. So it's not computationally heavy as well. So this kind of computation, we can just push it into the edge with the clients. That can be done. So another the setup that we can do is main server also can do the tasks of Fed server. There is no need of introducing the new Fed server. But as Amin mentioned, that means yes, main server, if knows about the aggregation, it knows about the full model. That's the another our focus, that means point to stop main server knowing the full models, knowledge of main models. So yes, the Fed server can, in this sense, Fed server and main server if collides, then we lose our arguments of this model privacy here, because main server will know the full model. So then we don't have. So what we can do is all these aggregations. If the gradients and everything and the computations of these aggregations is based on the homomorphic encryptions, we can push everything to the main server. We can offload everything to the main server, and then main server will not know this one. But as I mentioned, that means if Fed server and main server collides, then we lose that argument of model privacy.
Encryption can help if
yes,
even if they are colliding.
We don't need Fed server anymore. But the thing is, we cannot push the computations to the edge with the clients, because we again need to rely with the main server.
Okay, good. My next question is, if there is no other question from the Zoom. So, okay. My next question is about the like increasing the number of clients, right? That K factor that you are increasing. And you had probably the next slide, you had something which was showing that, yeah, so a split Fed learning version 1 and version 2 will have less amount of data being downloaded, and they will also have less in time spent on the model. But something that probably is not captured here is the communication round, right? So as I think it's more apparent in your once you are explaining the version 1 versus version 2, there are all these communications between clients and the main server, and also from the Fed server to the clients, right? So the more split the data, I think, and the more user you have, the number of users in between, then you have increased the number of rounds, right, of communication. But have you also tested that in a network? Like, did you have like a server totally separating for the Fed server and then another server, and then all these users, all of these was done in one computer, and there was no propagation or delays or latency for the network? Or
nice question. That's from the implementation side. So what we did for this time measurements is it's different than the other simulations that we have. So the performance and other things. For the time measurement, what we did is we have these virtual networks, virtual machines. So one virtual machine, but it's in the same high performance computing platform. So they're all wired connected. So the practical, scenarios of communications are not captured in this experiments. And we also assume that all the clients that whatever it's participated, they are fully participated. That means every round, we don't lose any client in this model training. That's also the case. So we have this virtual machines for running this program for server as a server. And we have the virtual machines, separate virtual machines. Let's say if 5 clients, then we have 5 virtual machines, each running its own, as a local, as a client, and then computing on their local data. That's how we did it for this time measurement here.
Thank you.
Thank you. If there are no questions, then I'd like to move on to the next part. So where it's second part, it's a bit more about the software vulnerability detections and might be in the interest of the participants as well. So the main purpose of this work is, as we know, that means we have lots of these days hearing about the performance, super performance of these transformer-based architectures, something like we heard this generative pre-training transformer GPT. GPT-3 is doing this one, GPT-3 is doing that one in the natural processing domain. So we're also quite fascinated by that one, and then try to see whether these language models, these transformer-based language models can be used or utilized for the software vulnerability detections. As we know that software like high-level programming languages, they're quite close to the natural language. And then we try to explore that thing in one of our works. So it's available on the archive. So in this part, we'll see from the data set, data translations, models, system flow, and then finally see the results. So in this work, what we did is we considered two data sets. That's all the C++ programs. The first one is the Waldpaper, we say it's Waldpaper data set. And then this type, the data set has two types of vulnerabilities in C++ related vulnerabilities. One is the buffer eater, the another is the resource management eaters. And the second data set is the semantic-based vulnerability candidates. That's the SAVC, we call it. And it has the multiple 126 types of vulnerabilities. And one type of vulnerability can have multiple this common weakness enumeration, CW is what we have. They can have multiple CW IDs with one vulnerability. And then how we can divide overall, in a broad sense, we divide this SAVC data set into 4 types. That's library 5 function calls. That's all associated with the function calls. And then our buffer eater and resource management eater also falls under this function call. That means API function call related vulnerabilities. And we have the array uses, pointer uses, and arithmetic expressions related vulnerabilities. We consider this one. And what we found is we have this data sets that's all collected from the open source C++ codes maintained by SARD and NVIDIA. That's a national vulnerability data set. And then the SARD is what we have this SARD is the software assurance reference data set. What we found in the Waldpaper data set is there is one work by Lee et al. As a first reference, which is published in NDSS 2018. They didn't mention, they didn't capture, I don't know. So they did not clean the data set. They never mentioned about this thing. But what we found is in that data set, many data sets are redundant data sets. That means redundant here means the same data set, same samples copied multiple times. So what happens is if we do the train and test split of this kind of data set, then the same sample can be in training, same sample can be in test. That's how the leakage happens. And in those kind of test data set, the performance might be better. So that's a false impression of more, the better performance. And then we also found that same sample can have the multiple different labels, and that's how it confuses to the machine learning as well. And then that's not good. So we removed the redundant as well as the these conflicting samples, and then we clean it, and then we split it into train and test into 80-20 ratio. And we perform both the binary classification tasks. That means if you go into the group 1, that's the only buffer eater and non-vulnerables. So we just try to see whether the sample is buffer. That's a classification task, and just the buffer eater or not buffer eater. We do the same for the resource management eater. And we also perform the multi-class classifications, like we combine these two data set. And then we see that means we give the label 1 to the binary eater, buffer error, and then the label 2 for the RME and label 0 for the non-vulnerable. That's how we did the multi-class. And the similar approach is used for this division and cleaning for this SAVE-EC dataset as well. And we carry on the experiments. So as we know, that means before inputting the data to the model, these transform-like models, it's need to be in the formatted form. It should be in some specific formats. So the first thing is you have given the source code, so how we make it suitable for these machine learning models, right? So one way is just read the 10 lines and then feed it to the model. Again, next the 10-line code snippets and feed it to the model, but that's not a good idea. So what is Lee et al., this multi-paper paper and this NDSS 2018 paper, what they did is they proposed this code gadget kind of thing. So what happens is we started from the, for example, we started from the library function API call. That's a string copy right now. And there's two variables. You can see it, string copy has buffer and str, buf and str2 variables over there. We backtrack the dependencies. Right? So we go, that means where this string copy, these variables are defined inside this test function. So if you go into line 5, right, there is a buffer is defined, its maximum size is defined, and then you go back to the line 4 where the max size is defined, and you go again back to the function, the test, and then where the pointer string, that's string is passed from the main, the functions or other function. Again, backtrack to the main, wherever its function is called, this test is called, and again, backtrack where this, the pointer is defined. So we backtrack to find the dependencies and we compile all the code. You can see it's on the right-hand side, backtrack to collect the semantically related program files and then compile it and then form the code gadgets. That's the first step. And that's how we take this, that means the snap that's extract from the source code to the code gadget level. So it's done for each API functions. And these code gadgets are labeled vulnerable or non-vulnerable, or which type of vulnerability. And then we do follow these word embeddings as well, because we are using the transform-based models. And then these code gadgets are transformed to the vectors of the suitable, the trained space, and then feed it to the models. So we, for the, let's see the models, and then I'll say that what kind of, the word embeddings are used for this specific models. As you can see on the left side, that's the architecture of these transformer based models. So it, let's not go in details, but what I'll say is it has two major components. One is the encoder part, and the another is the decoder part. And then all these models on the right-hand side table are based on this model, this architecture. And somehow we know that means this transformer-based architectures, model based on the transformer, are performing pretty well compared to the other recurrent neural networks like BiLSTM or BiGRU. That's a long-term, short-term memory, bidirectional gated recurrent units, those models. We can categorize these models into two types. One is bidirectional encoder represented from transformer, that's BOT model. It's just the encoder based model. So it doesn't have the decoder block here. And then the GPT, that's a generative pre-trained transformers. They are only the decoder based blocks. So they don't have the encoder blocks at all. The performance, their working principle is also a little bit different. So BOT uses all the sequence input at one time, but the GPT, they always one token at a time to its input, and it's always looking the backward direction for this, the finding the relationship or the understanding, inferring about these inputs, whereas the BOT, it inputs the whole tokens of the whole, the sentence, and try to go back and forward both direction for each of these tokens. So token means if you have the has, if you have a sequence, that means the sentence which has a sequence of the words. So each word can be considered as a token, so which has semantically some meaning. Those can be split. But they use this word piece-based tokenizers and embeddings. GPT, they use this byte pair, byte label, byte pair encodings that pretend on the natural languages words, and then the space is a little bit different in vector space. And then this BioLSTM and BioGRU, they use this word-to-vec embeddings. So that means each token is mapped to those vectors which are pre-trained, and that's how those embeddings are pre-trained, and that's how it's mapped to the specific vector before feeding it to the models. And this Megatron, the interesting thing about Megatron is this proposed by proposed by the NVIDIA. What they did is keep increasing, because there is a trend of increasing size in this transformer-based models, so BOT, GPT, and then they are saying that in our consideration also we started from the 1.2 million models up to the 6 billion models parameters. And so it's starting increasing. If you think about the GPT-3, it has, I think, I don't know, 60 billions or something like that. Model parameters. So it's pretty difficult to train these models on the limited with the limited GPU capabilities. Even it's not possible with high performance computing, where there's limited something like, for example, 16 gigs of GPU memory. So still it's difficult with those kind of the environments. So we need the higher GPUs with a higher memory, something higher than 48 gigs inside the memory, this sort of thing. So that's why the NVIDIA, what they did is in the architectural level, intra-layer parallelizations, they enable the bot, they change that one to the bot and GPT, and then they have this Megatron bot and Megatron GPT-2 models proposed. So we consider also, let's see, that means how we do the trainings or leverage these transformer-based models and the software vulnerability detection. So firstly, we take all the pre-trained transformer models, and then we added the classification heads. So on the right-hand top table, we can see what sort of architectures. It's just a fully connected classification head, because our task is now classification. So we add it to the transformer, and then we fine tune on this our code gadgets or the software vulnerability data sets. These mechanisms of transferring the models from gained in one domain natural language to the related domain that we call the transfer learning. And pre-train usually happens in the unsupervised fashion, because you give the one full sentence to the model and then max some of the words, and then you ask the model to predict that word. That happens in the pre-train. So that's how they know, that means what the sentence structures, grammars, and everything. And then in the fine-tuning is the supervised one, because we know that is what level of the code gadget is, and then we try to ask the model to predict that one. So in this one, we can carry on two ways. So one is we can freeze the transformer layer models parameters, and then we can only tune the classification level, classification head. That's one way. Or we can allow the changes in the transformer-based models as well classification heads for the bit. But we applied the second latter one. That means we allow the transformer-based models and then the classification head changes with the very low learning rate to fine-tune these models for the to capture and the adjustment with these code gadgets or our programming source codes. And then the trained models is tested on the code gadgets. So these are the results, and it's interesting that to find that the models, the transformer-based models, though even only fine-tuned for 10 epochs, are already showing the better performance than the existing BioLSTM or BioGRU-based models, which seem to be the state-of-art models. Though there are some works based on the bot which shows these performance improvements, but there were no works that's where the GPT-2 leverage the GPT-2 into the software vulnerability detections. So we can see that that's pretty good in terms of all performance if we consider this first data set, that is multi-packer data set, both in the binary classification as multi-class classifications. And you might wonder, that means another thing is there is a trend, as I mentioned, that is we have the big transformers models coming every month or so, and then saying that this beating outperforming the other thing, and whether do we have the similar pattern or not. And then we have this for the F1 score, particular F1 score. And we can say by observing this one is, though we have some ups and downs in this increasing model size, but we can see the increasing trend with the increasing model size, and might be we are just limited our experiments fine-tuning up to the 10 epochs. Maybe if we increase our maybe if you tune the hyperparameters separately differently, then might be we have that result here as well. But the takeaway message is we have the better performance with the transfer-based models, and transfer-based models are useful in the software vulnerability detections. There is another experiment that we performed, that is what's the model tuning time? Because if you wonder, that means how to choose, because there are lots of models in the transfer-based models, and which model to choose to do the vulnerability detections might be one factor can be the performance, the another factor can be the model training time. And as you can see, we have GP as the parameters increase, that means model training time also increased. So it also depends on the dataset size. So that's why we have this group 3 datasets, which combine of both as the longer time for GPT-J, but pattern is similar. So if group 2 has the smallest size of the dataset, and then the group 1 has a little bit higher than the group 2. So that's why we have that pattern, but we can see the pattern, and it's pretty obvious as well. So there is a trade-off. If you trade off in between the what is allowed for the model training and what's allowed for the performance, we can actually have some sort of choices of these models for the vulnerability detections. So this is the performance for the CBC datasets. So we only consider the bot base and GPT-2 base for this experiment. There is no particular reasons why we didn't choose, but we didn't have that much time to run the other higher big models. That's why we only have these 2 models. But the thing is, we tried with our BGRU models as well, based on the explanation of the previous works and whatever the results that is reported in the previous works. So if you see the F1 scores, F1 score pretty, that means which reflects both the false positive and false negative. That's again, the transfer-based models are better, but particularly if we go into the false negative or false positive, then that might not be the true. Still it's open to explore more, but the balanced metric, something like F1 score, is still better. Finally, that means with the interest of time, I'll not go explore more on that part, but I would like to take this opportunity to advertise our opportunity. And then it's a nice opportunity. I think it's a collaboration between our group, that's a distributed system security group, and then the Monash University. So these we have 3 positions available right at this moment. So these are separate from the Data 61 scholarships, and it provides the full scholarship for the students. And the topics that's related to the quantum, so quantum-inspired machine learning for improved cybersecurity, that's quantum machine learning domains and quantum cybersecurity. So the team, the Said Khamtape, Usman, and then the Hazimi and myself is in the team. So if you have any strong candidates, it's no need to have the quantum experience, but if they have the machine learning experience and would like to explore the quantum, please let us know. That's a good opportunity for us to collaborate. So application closes on the 30th November. So this all about how two of these works. And thank you, Amin, and thank you, Mohammed, once again. So if you have any questions related to second part or scholarship, please let me know.
Thank you very much, Chandra, for your very interesting talk. Maybe we ask the Zoom participants first if they have any questions. Anyone from the Zoom has any questions? How about in the physical room? Are there any questions for now?
Nothing from my side.
Yeah, I might ask actually. I'm actually wondering about this. Like, do you know how much kind of like progress is made in terms of this quantum machine learning side? I mean, this is not really what you talked about, but yeah, I'm kind of curious about it.
So sorry, Mohammed, can you repeat your question?
So how much progress is made in terms of this quantum machine learning? Like, has there been any kind of like work that show that in the quantum machine learning same thing you can do things much more efficiently, or you can do things that were unknown to be done by classical computers or something?
Pretty much it's happening in this quantum machine learning domain as well. So far what I know is if you really want to implement in the quantum machines, it's very time consuming and almost what to say, it's not efficient directly go into the quantum machines and do the machine learning. But what's happening is it's in the emulator space. So we have these quantum machine algorithms, simple SPMs, simple linear regression type of algorithms. They design the circuits, quantum circuits, and then based on those algorithms, and they try to run on that one emulators. So that's they have the results on this one. So other are transforming the classical domain data into the something like, because it's a bit representations, kind of making analogy, right? So if we have right now we have just a bit 1 and 0, but in the quantum we have this fuzzy state. So that's why we have the 2-bit representation. 0, 0 means 1, 0, 1 means another, and then the 1, 0 means another. Something like that, where we can transform the data from 1, 0 to 2-bit representation, and then perform the experiments, just making it close to the machine learning, the quantum computing, and then doing the experiment. This also finds the, because we are transforming the data from one domain to another domain, that's some works have already shown that means the machine learnings are quite efficient in those, because we increase the freedom from 1, 0 to degree of freedoms to the going to the 2 bits. And that's why also they are showing that degree of freedoms also has some effect on the decision making of this machine learning. So it's quite happening in this domain actually. It's not like nothing is there. So
yeah, it's a very interesting domain. Okay, I think in the interest of time, if there are no more questions, we may conclude the session here. Thank you again, Chandra, very much for your interest in
Thank you, Mohammed.
And yeah, thank you everyone for tuning in, and we will hope to see you in the next seminar. Thank you.
Thank you.